Space is a vast and silent expanse, a canvas upon which billions of years of cosmic history are painted in light and shadow. Among the countless celestial objects that drift silently through the void are asteroids, remnants of the early solar system that never coalesced into planets. These ancient rocks, ranging from tiny grains to enormous bodies hundreds of kilometers across, carry the story of a time before Earth, before Mars, before even the Sun reached its full brilliance. While many asteroids are composed primarily of rock or ice, a rare and mysterious class exists: metallic asteroids. These objects, gleaming with iron, nickel, and other metals, are relics of planetary cores that were stripped away and left to wander the cosmos, their origins steeped in violence, chance, and cosmic fortune. The study of metallic asteroids is not merely an academic pursuit. They offer a glimpse into the inner workings of planets, the history of collisions in the early solar system, and perhaps even the future of human exploration and resource utilization beyond Earth. These metallic wanderers challenge our understanding of planetary formation, present tantalizing possibilities for mining rare metals, and pose deep questions about the very nature of our cosmic neighborhood. The journey to understand metallic asteroids begins with understanding their place in the broader classification of asteroids. Astronomers broadly divide asteroids into three types: carbonaceous, rocky, and metallic. Carbonaceous asteroids are rich in organic compounds and water, representing the primordial building blocks of the solar system. Rocky asteroids, often silicate-rich, form the bulk of the asteroid population, bearing resemblance to terrestrial rocks. Metallic asteroids, however, are rare and enigmatic, believed to be the exposed cores of protoplanets shattered by violent collisions in the early solar system. Their reflective surfaces distinguish them from their darker, carbon-rich counterparts, hinting at the dense metals hidden within. The origins of metallic asteroids trace back to a turbulent era when the solar system was young and chaotic. Roughly 4.6 billion years ago, countless protoplanets, large planetary embryos that could have become full-fledged planets, collided with one another in a frenzy of destruction and creation. Some protoplanets merged to form larger planets, while others were destroyed, leaving behind fragments of crust, mantle, and core. The metallic fragments, composed primarily of iron and nickel, became what we now identify as metallic asteroids. In essence, these objects are the skeletons of lost worlds, remnants of planetary cores stripped bare and cast into the void. Among the most famous metallic asteroids is 16 Psyche, located in the main asteroid belt between Mars and Jupiter. Psyche is remarkable not only for its size, estimated at 225 kilometers in diameter, but also for its unusual composition. Unlike typical rocky or carbon-rich asteroids, Psyche appears to be composed almost entirely of metal, suggesting that it is the exposed core of a protoplanet that once existed in the early solar system. NASA has recognized its significance and launched a dedicated mission to study Psyche, aiming to unlock secrets about the formation of planetary cores and the history of violent collisions that shaped the solar system. The potential value of metallic asteroids like Psyche extends beyond scientific curiosity. If their metals could somehow be harvested, they could represent trillions of dollars in resources. Iron, nickel, cobalt, platinum, and even gold may be locked within these wandering cores, waiting for humanity to reach out and claim them. Yet metallic asteroids are more than floating treasure chests. They're natural laboratories, offering a unique window into processes that are otherwise hidden beneath the crusts of planets. Studying these objects can illuminate the processes of differentiation, where planetary bodies separate into core, mantle, and crust. Each metallic asteroid is a preserved core, a piece of a planet that allows scientists to study planetary interiors without drilling deep into Earth or other worlds. These objects can reveal the thermal, chemical, and mechanical history of planetary formation, offering clues about how planets evolved over billions of years. The surfaces of metallic asteroids tell their own story. Some are smooth and featureless, while others are scarred with craters, fractures, and irregularities, evidence of a long history of collisions and space weathering. Many metallic asteroids are not composed of pure metal, but are coated with layers of silicate rock or other materials. This outer layer may result from micrometeorite impacts, solar radiation, or remnants of the original protoplanetary mantle. Determining the thickness and composition of these layers is crucial for understanding the asteroid's history, its exposure to the harsh environment of space, and the processes that shaped its evolution. Spectroscopy is the primary tool scientists use to study metallic asteroids. By analyzing the spectrum of sunlight reflected from an asteroid surface, researchers can detect the presence of metals such as iron, nickel, cobalt, and platinum. Some metallic asteroids display unusual metal ratios, indicating exotic formation processes or the influence of ancient cosmic events, such as nearby supernovae that seeded the early solar system with heavy elements. The study of these compositions raises profound questions. How did these metal-rich bodies acquire such diversity? Were they forged entirely within protoplanetary cores, or do they also incorporate material from stellar explosions predating our Sun? These questions lie at the intersection of planetary science, astrophysics, and cosmochemistry. Metallic asteroids may also offer clues about magnetic fields. Some are believed to have generated magnetic fields in the past, remnants of the dynamo processes that occurred in their parent bodies. By studying the remnant magnetism preserved in metallic asteroids, scientists can reconstruct the early dynamics of planetary interiors, offering insights into how magnetic fields influence planetary evolution. These small objects may thus illuminate processes that shaped not just planets in our solar system, but potentially planets around other stars. The rarity of metallic asteroids makes them especially intriguing. While rocky and carbonaceous asteroids number in the tens of thousands in the main belt alone, metallic asteroids represent only a small fraction. Each metallic asteroid has a unique shape, rotation, density, and surface composition, making it a one-of-a-kind cosmic relic. Their irregular rotations, cratered surfaces, and varying reflectivity suggest individual histories shaped by collisions, thermal stresses, and space weathering, meaning that each one tells a story that cannot be generalized across the population. Technological exploration of metallic asteroids is a formidable challenge. Their density, gravity, and surface properties pose difficulties for spacecraft landings and sampling missions. Even small errors in navigation or propulsion could send a probe spinning into space. Missions like NASA's Psyche are pioneering techniques to study these bodies remotely, using orbiters to map the surface, measure magnetic fields, and infer internal structure without direct contact. The data gathered will not only reveal the composition of the asteroid, but also offer insights into the processes that formed planetary cores across the universe. Metallic asteroids also hold potential implications for humanity's future. The prospect of mining these objects has captured the imagination of scientists, engineers, and entrepreneurs alike. Extracting iron, nickel, and platinum from asteroids could revolutionize industry on Earth and provide resources for future space exploration. However, the technological and economic hurdles are immense. Mining spacecraft must operate in microgravity, deal with extreme temperature fluctuations, and process materials far from Earth. Moreover, ethical and legal questions loom. Who owns these resources? How should we regulate asteroid mining to prevent conflicts and ensure equitable access? The study of metallic asteroids is thus intertwined with questions about our place in the cosmos, our responsibility to the solar system, and the ways in which humanity might expand beyond Earth. Some metallic asteroids may even hold clues about the origin of life. Iron, nickel, and other metals are essential for certain catalytic reactions that could have contributed to the emergence of life on Earth. Collisions between metallic asteroids and early Earth may have delivered not only metals, but also complex chemical compounds, seeding our planet with the ingredients necessary for biology. While this idea remains speculative, it highlights the profound connections between these distant objects and our own existence. The mysteries of metallic asteroids extend beyond their composition to their behavior in space. Many rotate at unusual rates, tumble chaotically, or display unexpected orbital characteristics. These dynamics provide clues to their mass distribution, internal structure, and history of collisions. By modeling their motion, scientists can infer the density, shape, and internal cohesion of metallic asteroids, offering indirect evidence of their formation and evolution. Over the decades, astronomers have cataloged hundreds of metallic asteroids, yet only a handful have been studied in depth. Each new observation brings surprises, from unexpected surface features to anomalous metal ratios. Some metallic asteroids appear nearly spherical, while others are elongated or lumpy, suggesting different formation histories or degrees of collisional fragmentation. The diversity within this small population continues to challenge existing theories of planetary formation. The study of metallic asteroids also intersects with the search for near-Earth objects that could pose threats to our planet. While most metallic asteroids reside in the main belt, some are perturbed by gravitational interactions and wander closer to Earth's orbit. Understanding their structure and composition is critical for developing strategies to mitigate potential impacts. A dense, metallic asteroid striking Earth will behave differently from a rocky or icy one, and preparation requires knowledge of these differences. Beyond the scientific and practical aspects, metallic asteroids hold a profound philosophical allure. They are remnants of planets that no longer exist, frozen cores wandering through space for billions of years. They remind us of the fragility and impermanence of worlds, the cosmic violence that shapes solar systems, and the incredible opportunities that await humanity as we venture beyond Earth. As our technological capabilities grow, metallic asteroids may become both a source of knowledge and a source of wealth. Mining, exploration, and even colonization of these objects could become part of humanity's future in space. Yet their greatest value may remain scientific. They are archives of planetary history, cosmic laboratories, and keys to understanding processes hidden beneath planetary crusts. In the darkness of space, metallic asteroids drift silently, carrying secrets from the earliest days of the solar system. Each scar, each surface anomaly, and each spectral signature is a message from the past. Missions like Psyche promise to decode these messages, revealing the hidden processes that forge planets, created magnetic fields, and determined the distribution of metals that now shape human civilization. In the end, metallic asteroids are more than floating chunks of metal. They are reminders of cosmic history, natural laboratories for science, and potential resources for the future. They embody the collision of past and future, science and exploration, danger and opportunity. They are silent witnesses to the violence and creativity of planetary formation, messengers from lost worlds, and keys to understanding the forces that govern our solar system. As humanity continues its journey into space, metallic asteroids will be both guides and destinations. They invite us to explore, to learn, and to marvel at the mysteries of creation. Each metallic asteroid is a chapter in the story of our universe, a story that began billions of years ago and continues to unfold, waiting for us to uncover it. As we look to the stars, the gleaming metal of distant asteroids reflects not only sunlight, but the promise of discovery, the allure of knowledge, and the endless curiosity that drives humanity to seek answers in the silent depths of space. The mystery of metallic asteroids is far from solved. Each new observation, each mission, and each analysis brings us closer to understanding these ancient relics. They challenge our understanding of planetary science, inspire dreams of space exploration, and connect us to the cosmic forces that shaped our solar system. Somewhere in the asteroid belt, 16 Psyche and countless other metallic wanderers drift in quiet orbit, holding secrets billions of years old. They are waiting for humanity to listen, to study, and to uncover the hidden history encoded in their gleaming cores. In pursuing the mystery of metallic asteroids, we pursue the story of our solar system, the history of planets, and perhaps even the origins of life itself. They remind us that space is not empty. It is a repository of knowledge, adventure, and infinite possibility. The metallic asteroids of our solar system are silent, patient teachers, waiting for the day when human curiosity will reach out and uncover their secrets, forever changing our understanding of the universe and our place within it.